Congratulations on finishing your first test in chemistry. Woo! Good work. We just released the stats this morning and they were very good. So congratulations. That means you studied well, you paid attention. Well done. So I hope you feel good about the score that you got. And if you didn't, remember that we have 2 tests in this course and your best test counts for the higher weight. So if you didn't get a score that you were as pleased with, know that test 2 is coming up and your best test counts for that 30-some% in this course. So keep doing your best, keep showing up for class, keep doing those practice problems, and congratulations on getting this test behind you. I hope you brought your model kit with you today. If you did, we're going to start by pulling out a couple pieces. Okay, so we have a bigger group today than we did on Friday, but when you open up your model kit, you will see a whole variety of different types of pieces. The piece that I want you to find is this straight one here. You should have 2 of these. You also have a whole bunch of different colored balls. You can choose your favorite colors today. They have thick ends and thin ends, and you can add them as you like. Okay, and I will give you 5 seconds to finish talking. 5, 4, 3, 2, and 1. Okay, you can hear I do not have an awesome voice today, so we'll keep it nice and quiet so everyone can hear. Okay, so if we have 2 regions of electron density around our central atom, this piece here represents the central atom. This can connect to other things, but here I've shown that this central atom is connected to 2 different atoms. This counts for 2 regions of electron density. Both of these, in this example, are bonding regions. They're a bond with this atom and a bond with this atom. And we can see that this makes for a linear molecule. From atom 1 to the center atom to the second atom, the bond angle here is 180 degrees, and this is linear, the simplest shape that we can come up with. Well, if we have 3 regions of electron density, we want to grab this triangle piece. And you should have 2 of these in your kit as well. You can add balls to indicate the atoms, or you can leave it plain, your choice. But here is my trigonal planar electron geometry. Right now, I'm showing the central atom is bonded to 3 atoms here. And since we have 3 regions of electron density, it has a trigonal planar geometry. If you lie it flat on your paper, you'll see that all of the atoms, the center atom and the 3 bonding atoms, lie flat on your paper. That's where the name planar comes from. The trigonal, of course, tells you 3. That's the 3 pieces. When we have 3 regions of electron density, whether they be bonding, a single, double, triple bond to an atom, or non-bonding, like a non-bonding pair of electrons, they adopt this trigonal planar electron geometry. And we can see the bond angles would be 360 divided by 3, which is 120 for each of the bonds. So red to center to red is 120 degrees. This is where we get the trigonal planar electron geometry. Now, if all of these regions are bonding, as I've shown here in the picture, if all of these 3 electron regions are bonding, then we would call this a trigonal planar molecule. However, if one of these regions was a non-bonding pair of electrons, I'm going to take the atom off, and now this is just going to represent a non-bonding pair of electrons. The electron arrangement still adopts a trigonal planar geometry because these non-bonding electrons take up space. However, when I go to name the molecule, I cover up with my hand the non-bonding electrons. They still take up space, so I still grab this trigonal planar structure, but I'm going to ignore this part when I give it a name. So now I have red to the center to red. Not quite linear, we would call this bent. And A molecule that has this structure is called bent. Now, remember, non-bonding electrons take up just a little bit more space. So it's pushing out on these atoms here. So the bonding angle between red, center red, is going to be just less than 120 degrees. Because this is non-bonding, it takes up more space, so we call it just less than 120. And that brings us from 2 to 3 regions of electron density, and we're going to pick up today at 4 regions of electron density. Before we do that, though, we're going to finish doing a few more examples with Lewis structures. So if we want to figure out the molecular shape of a molecule or a compound, well, we need to start with the Lewis structure. Lewis structure doesn't tell us bonding angles, it doesn't tell us shape, but it does tell us single, double, or triple bonds. It does tell us non-bonding electrons. So it tells us about the electron locations. From the Lewis structure, knowing single, double, triple, and non-bonding electrons, we can figure out the total number of electron regions, total number of regions of electron density, and that tells us the electron arrangement. From there, depending on if we have some non-bonding regions, we can give it a name, the molecular shape a name. So we're going to jump in with this example here. We have a structure. We already did BF3 on Friday, so you can look that up on OWL. I got that posted this morning. And we're going to start in with nitrate, NO3 negative. We want to figure out what the shape of this polyatomic ion is. Now, to start figuring out the shape, we need to start with the Lewis structure. As I mentioned on Friday, for all of these examples in 3.2, we're only going to do Lewis structures for a couple of them and work through them because that was a topic from 3.1 and we already know how to do that. However, nitrate is a really interesting example, so we are going to work right from the top, Lewis structure to electron arrangement to shape. So let's start with the Lewis structure. We'll count up the total number of electrons that we have to play with in this ion. So we would expect nitrogen to have 5 valence electrons. We have 3 oxygens, each with 6 valence electrons. And we can see this this ion has an overall -1 charge, so that's an extra electron to add. And that brings us to 24 electrons to play with. I like to work in pairs, so that gives me 12 pairs of electrons. Well, I have 1 central atom and 3 atoms surrounding it. That's my skeleton structure. To draw the skeleton structure, that uses up 3 pairs to have those minimal number of bonds, which leaves me with 9 pairs of electrons to add to the shape or add to the structure. So I'm going to start with the outside atoms, my more electronegative atoms, and give them each a filled octet. So starting with the oxygen on the right, it already has 2 electrons from that single bond. So I'm going to add pairs of electrons. 1, 2, 3 pairs of electrons, 2, 4, 6. That brings it to 8 electrons. 4, 5, 6, filled octet for that oxygen. 7, 8, 9. And we've used up all 9 electrons, no more electrons to go on the central atom of nitrogen. However, nitrogen still needs a filled octet, so I can take one of these pairs of electrons from oxygen and turn that into a double bond. And when I do that, nitrogen will also have a filled octet. I'm going to redraw the structure here so we can see all of the bonds. Now, when I check for filled octet, I can see each atom has a filled octet. When I go for formal charge, the central atom, nitrogen, we would expect it to have 5 valence electrons, and it can claim 4 bonding electrons, so it has a +1 formal charge. The oxygen with a double bond has a formal charge of 0, 6, -2 bonding electrons, -4 non-bonding electrons, brings it to 0. And then the oxygens with the single bond, we would expect it to have 6 valence electrons. It has 6 non-bonding electrons, 1 bonding electron, which gives it a -1 formal charge. So both of the oxygens with single bonds have a -1 formal charge. Now we're back to that kind of funny formal charge splitting in this situation. If nitrogen was bigger, we could start to share more electrons and give it an expanded octet. However, nitrogen is in the second period. It's too small to have an expanded octet. We can't give it any more bonds. Therefore, we do have this kind of funny splitting of formal charge, and this is the best we can do. We can see the sum of the formal charges, -1 plus -1 plus +1, still gives us an overall -1 charge, which matches the charge of nitrate. So now we need to go from the Lewis structure to the electron arrangement. For counting electron arrangement, I don't care if it's a single, double, or triple bond, all of those just count as one bonding region. So for the central atom, I count 1, 2, 3 bonding regions. So I have 3 regions of electron density around the central atom. I can see that all of them are bonding regions. Therefore, I pull up my trigonal planar structure, 3 regions of electron density. All of them are bonding, so all of those atoms we need to consider when we're naming it. Therefore, it is called trigonal planar. And we could classify this as an AX3 molecule, the central atom, 3 bonding atoms around it. So I'm going to leave that one up. That was nitrate. Now for you, I'm asking you to solve what is the shape for nitrite, NO2 negative. Work with the person beside you, draw that Lewis structure, and figure out its shape. Now, just so you know, we do realize it's warm in here. We have contacted facilities management about the temperature in this room. We'll appreciate it come December, I'm sure. Okay, you can compare your Lewis structure to the Lewis structure on the screen. Think about electron arrangement and determine shape. And 10 more seconds. And 3, 2, and 1. Okay, most going for C. A few people chose B. So here we have 3 regions of electron density. 2 of them are bonding, 1 of them is non-bonding. So all 3 of those regions contribute to the electron arrangement. We have 3 regions of electron density. 2 of them are atoms. 1 of them is a non-bonding pair of electrons. So we pick up this shape, figure out what we're left with, what we can see, and we can see it is a bent structure. Even though there are 2 atoms, it's not linear like this one. This one doesn't have any more non-bonding electrons contributing to the shape. Nitrite does have a pair of non-bonding electrons, and so we need to pay attention to that shape. If we overlay these, linear and bent, we can see they certainly have different bond angles. Okay, so let's move along now to 4 regions of electron density. For this one, I'm going to ask you to get 2 of your black pieces from your kit. Now, this is the one that you have the most of because these are the pieces that make up the backbone of organic molecules. This is often the carbon atom that has 4 single bonds. So grab 2 of these pieces, and you're going to put these kind of U shapes together, fold them into one another, and push and pull until you hear a click. Okay, there should be a nice little snap, and then you have your tetrahedral shape. Now, I hope that you brought your model kit with you today. If you didn't, your homework for today is to go home and build all the shapes. You're allowed to bring this model kit pre-built into the final exam and into your tests. So building these shapes ahead of time is a huge bonus for you, so learn how to use them. Okay, so we have a tetrahedral shape here. I know, it's exciting. You can put atoms on them if you want. Those are optional. Okay, and 3, 2, and 1. So I hope you have one of these structures in front of you. If you lay 2 of the red balls and the central atom on a piece of paper or on your hand, you can see the bond angle from red to central to red. You can lay 2 of these bonds in the plane of the paper or in the plane of your hand, but then you'll see one is jumping out towards you and one is going away from you. If we rotate and lay 2 different ones in our hand, we can see again the same bond angle. It's 109.5 degrees, and one prong coming towards you, one going away from you. And every way we rotate this, we have the same 109.5 degree bond angle. Now we can draw that by showing the bonds in the plane of the page as well. Now, why is it called a tetrahedral? Well, it reminds us of a tetrahedron. If we took 3 of these balls and made a face and made a surface and made a surface and made a surface, we would have a tetrahedron, one of the shapes you would have learned a long time ago. And it has 4 sides, 4 vertices, and that makes our tetrahedron shape. So if all of these bonding regions are atoms, then we name the molecular shape based on the presence of all of these atoms. And we would call this a tetrahedron or a tetrahedral shape. If, however, one of these atoms or one of these electron regions is not a bonding region, if it's not an atom, if this is just a non-bonding pair of electrons, this still takes up space. It actually takes up slightly more space than a bonding region. But when we want to name the shape, we hide that non-bonding region. And now we have to come up with a name for what's left, the central atom with 3 atoms around it. Now, this one is called trigonal pyramidal. So it's a triangle pyramid. You can see it's a pyramid because it has 3 sides here as a triangle bottom. So if you just look straight down, it looks like a triangle. But if you tip it sideways and look all of those 3 atoms, the red balls, you can see the central atom is not on the same plane as the red atoms. So it's not trigonal planar, but it's trigonal pyramidal. We could call this one AX3E1, and I will add that to my notes afterwards. Well, if two of these regions are non-bonding, then we need to take away a second atom. Now we have a non-bonding pair of electrons here, a non-bonding pair of electrons here. And if we cover both of those up, we want to name the molecule that's left just based on the two external atoms and the central atom. Now this one reminds me a lot of the one that we have over here where we started with 3 regions of electron density. This shape is also called bent. So even though we started with 4 regions of electron density, if 2 of them are non-bonding, we end up with a bent shape. Okay, I'm going to freeze this for a second. And I would like you to identify these 4 molecules. Work with the person beside you for 1 minute and identify their shapes. Figure out the axe notation and their shapes. Okay, so identifying these Lewis structures. These are structures that are all based on 4 regions of electron density. Methane here would be AX4 and tetrahedral, as I'm sure you all found out. Ammonia also has 4 regions of electron density. 3 of them are bonding regions. 1 of them is non-bonding, so this is trigonal pyramidal. Note that it is not planar, it's not trigonal planar, it's not flat, but it is a pyramid. And then we have water, which is our AX2E2, and this is bent. So notice we've come to the molecular shape bent from 2 different electron geometries. Okay, so let's jump along here. We have done 2 regions of electron density. Hold on to that one. We have done 3 regions of electron density. Hold on to that one. We have done 4 regions of electron density. And now we're ready to go to is probably the most complex shape. I want you to find your second straight piece that looks like this. And then find your second triangle piece. If you can't find them, you can use the 2 that you started with. So you're going to take the trigonal planar piece and the linear piece and stick them together and push and pull until you hear a little snap. Then it's really helpful if you label the straight piece with 2 colors. So the part that just goes straight up and down, we can label with 1 color. And the trigonal planar piece, choose your next favorite color and label that here. Now this molecular shape, or this electron geometry, is a little more unique because it has different bond angles. Now, if you've built this structure, these are your axial pieces, the one that go up and down. And these ones, the triangle ones, are your equatorial. They kind of lie in the equator, if this was our globe. Now, if I go from axial to my central atom to an equatorial, if you look at that bond angle, we can see this one is 90 degrees. If I rotate here, you can see this one is 90 degrees as well. If I rotate it again, 90. So all of these angles are 90 degrees. However, if we rotate it this way and we look straight down the axial piece, we can see from green equatorial to central to green equatorial is 120 degrees. And same with this one, 120 and 120. So we need to be able to identify all of these different bond angles. Now this electron geometry is called trigonal bipyramidal. So trigonal, because it has that triangular equatorial piece. Pyramidal, because it's like a pyramid. If we take the faces, the triangular pyramid, it's like we have a top triangular pyramid and a bottom triangular pyramid if we filled in these faces. We stick two pyramids together. Bicycle, that's two. We've taken two triangular pyramids, smushed them together, so we have a triangular bipyramid, or a bipyramidal. And you need to be able to identify where those different bond angles are. So, question, chat with the person beside you. Based on Vesper theory, which we introduced on Friday, which of the indicated regions would most likely be occupied by a pair of lone electrons, a lone pair of electrons? Would it be one of the green equatorial pieces or one of the blue axial pieces? Chat with the person beside you and use your model to provide proof. And I'll give you 10 more seconds. And 3, 2, and 1. Okay, we have about half of the class going for B, and we're split between A and C. Let's think about this. If you have your structure in front of you, this is going to make more sense. If you're sitting beside someone who likes to share, maybe they will help you look at their molecule as well. This little green ball in the equatorial position, this is kind of, if I match it to the answer on the iClicker, it's the one in my left hand here, the B. This ball here has a 90-degree angle with the upper axial, a 90-degree angle with the lower axial, but when I look at it this way, it has 120 and 120 space. So it has 90 and 90 and 120 space to itself. If I look at this axial ball, the top one, option A, it is 90, 90 degrees, and 90 degrees. If you were a lone pair of electrons, you would know that lone pairs of electrons like to have a little bit more space. They're only attracted to one atom rather than being shared between atoms. So if we have a lone pair of electrons, it wants as much space as possible. If this was a lone pair of electrons up here in this axial position, it would only have 90 degrees of space all around. But if it was one of these equatorial, it would have 90 degrees this way, but it would have 120 degrees this way. It would have more space. Non-bonding pairs of electrons like to have more space. So if we have a non-bonding pair of electrons, when we have 5 regions of electron density, it is going to occupy one of these equatorial spaces. So going back to the trigonal bipyramidal, if all of those electron regions are bonding, we could classify this as AX5. If it's all bonding, all of those electron regions, and we would call it trigonal bipyramidal, the same as the name we use for the electron arrangement. However, as half of you identified, if one of these regions is non-bonding, this time it does make a difference which region we choose. I'm going to choose one of the equatorials because it has more space. So it's still based off of 5 regions of electron density, but now only 4 of these are atoms. One of them is a non-bonding pair of electrons. Now, if you were ruler of the universe, what would you call this shape? If you have it in front of you, what would you call it? Let's see, it is an AX4 E1, or just E. Has anybody gone to the park before and gone on like a seesaw or a teeter-totter? If you have this molecule in front of you, can you turn it into a teeter-totter or a seesaw so it can tip side to side? Because the non-bonding pair of electrons, we don't consider that anymore when we're giving it the name. It still takes up space, but it turns into a seesaw, a teeter-totter. And so that's the name that we give it, a seesaw. I always like it when the names make sense, and this one's great. Okay, if we had a second region of non-bonding electrons, so one of these regions of electron density is not bonded to an atom, well, for the same reason that we took off the first, I'm going to take off another equatorial region. So now we have two pairs of non-bonding electrons. They still take up space, so they're still contributing to where these other atoms are located in three-dimensional space. But now, when I name it, I'm going to hide those non-bonding electrons, even though they're contributing to the shape, and we want to give it a name. What letter of the alphabet does this remind you of? A T. It's a capital T, and this one is called T-shape. Someone was not feeling very creative the day they named this one. Okay, and if we had to take away another atom, turn one of these electron regions into a non-bonding region, we now still have our two bonding atoms, and we have three non-bonding regions of electron density. When we name the shape, we're just looking at the atoms. So I look at the blue ball, the central, and the blue ball. Does it look straight or bent? It looks straight, right? From blue to central to blue, we can see that it is linear. Just kind of like the linear one that we started off when we had two regions of electron density. This one is also linear. It's linear because it has three non-bonding regions that are contributing to its shape, but we call it linear. Okay, so let's start at the top, draw the Lewis structure, and figure out the shapes for these atoms. So we're going to start here with SF4. So we're going to do this one from the top and then jump right to the structures for the other ones. So for sulfur, we would expect it to have 6 valence electrons. We have 4 fluorine atoms, each with 7 valence electrons. No charge on this structure, so it should have 34 electrons, or 17 electron pairs. So my central atom and 4 fluorine atoms around it. The skeleton structure uses up 4 pairs of electrons, which leaves me with 13 electrons left to place. I'm going to start with the more electronegative outside atoms and give them each a filled octet. So 1, 2, 3 pairs to this fluorine, 4, 5, 6 pairs to that fluorine, 7, 8, 9 to that one, 10, 11, and 12. That leaves me with 1 pair of electrons to place on the central atom. So, by show of hands, what shape is SF4? Chat with the person beside you for like 10 seconds. We're just going to vote on this one. Okay, and 3, 2, and 1. Who votes for A, tetrahedral? Okay, no one did. That one's a little convincing because it does have 4 atoms bonded to it, the central atom. But no, what about B, C, D, E? And E wins indeed. Well done. So we have a seesaw structure here. It has 5 regions of electron density, but only 4 of those are bonding. So we could write this as AX4E1 as our AX notation. Well done. Okay, let's do this one now. Here we've drawn the Lewis structure already, ClF3, and we can see the non-bonding pairs of electrons. Here we can count up the bonding regions and the non-bonding regions and see that it has an AX3E2 structure. That's its electron arrangement. Since only 3 of these are bonding regions, we can call this T-shaped. And for the last one, this one is going to be an eye clicker. What is the shape of I3 negative? Chat with the person beside you and submit your answer. And 10 more seconds. And 3, 2, and 1. Okay, most people going for B, and I agree with you. We had a lot of votes for bent, so let's chat about that as well. So this structure here has the notation AX2E3. The number of bonding plus non-bonding regions is 5. When I know that I have 5 regions of electron density, be they bonding or non-bonding, I'm going to pick up my trigonal bipyramidal shape. I'm not going to get suckered into picking up the 2 or the 3 based on the number of atoms that are bonded to the central atom. I pick up my shape based on electron arrangement. I have 5 regions of electron density, so I need my trigonal bipyramidal to start from. However, only 2 of these are bonding regions. The 3 non-bonding pairs of electrons are hanging out in the equatorial plane, in that triangle there. That pushes the 2 bonding regions directly opposite from one another, and when I give it a name, we can see that it matches the linear shape. So that's why it's linear and it's not bent. The 3 non-bonding pairs of electrons are equally repelling it, so it's perfectly straight. Thumbs up, that makes sense? Okay, let's keep moving on. We are on to our last shape. We have done 2, 3, 4, 5, and we are ready for 6. So find your 2 bright pink pieces in your model kit, and we are going to complete our regions of our electron density. So something that really confused me for a while, and 3, 2, and 1. Thank you. Something that confused me was why 6 regions of electron density was called octahedral. An octopus has 8 legs. An octahedron has 8 sides. But we have 6 regions of electron density. When you pick up these pieces, you can stick them together, put the U shapes together, twist, push and pull until you make this shape here. If you count the number of prongs, it has 6. 3 here and 3 here. So 6 regions of electron density. However, if you drew a face or like a flat plane from this triangle and this triangle and this triangle and this triangle, and the bottom sides, you would see that the shape that you make has 8 sides to it. So the name of this shape isn't based on the number of prongs or the number of regions of electron density. It's based on the number of faces on the shape that would be made if you just paid attention to the faces. It has 8 faces, so it's called an octahedron. To get 8 faces, we only used 6 regions of electron density. When we analyze this shape, we can see it has 4 faces up here, so it's like a square pyramid with a square base if you looked straight down one of the prongs. And then it has a square pyramid on the bottom. Why it is not called square bipyramidal? I don't know, I didn't get to help choose the name. But it is called an octahedron because it has 8 faces. Question for you. This is just going to be a raise your hand question because we've done a bunch of eye clickers already. Based on VSEPR theory, which is valence shell electron pair repulsion. If you remember what it stands for, you can remember what the theory means. Which region, A or B, would be most likely occupied by a lone pair of electrons? If one of these regions was non-bonding, which one would it be? Chat with the person beside you. Okay, and by show of hands, who votes A, the one on the top? Who votes B, the one on the side? And who votes C? And I agree. Most people went for C. Why? Well, this time, whether you look at the shape this way, or rotate it this way, or flip it this way, it's all symmetrical. All of these bond angles here are 90 degrees. We're not going to get a different bond angle by rotating it. So choose one, doesn't matter. The first one can go anywhere. So if all of these are bonding, if this is an AX6, we call it an octahedral or octahedron. But if one of these is non-bonding, choose whichever one you want and turn it into a non-bonding pair of electrons. Now we need to give it a name. It still has this electron arrangement, but one of these regions is non-bonding. If you had to come up with a name, try holding your shape in your hand, hold the bottom prong, see if you can see the bottom square. So if you look straight down, you can see we have a square here. And if we connected the sides, we have a square pyramid. It has a square base and it is a pyramid. So this would be called square pyramidal. Why? Well, it has that square base and it's a pyramid. That non-bonding pair of electrons can really go anywhere. So where does the next pair of non-bonding electrons go? I want your attention for like 60 more seconds, so hold on. If one of these is non-bonding, does it matter? We're going to go by show of hands. Does it matter if I choose one of the squares versus the one on the top? Who says it does not matter? Who says it does matter? And I agree, it does matter. You can choose whichever one you want. Flip it over, whatever. Grab one. First one doesn't matter. Second choice does, because now all of these regions of electron density are no longer equal. This one could have a whole lot more space, and it'd be further away from the other non-bonding pair of electrons. So one of the opposite is going to become a non-bonding pair of electrons. What are we left with? Well, I can see I have a square. All of these pieces lie on a plane. So this is square planar. And that's what we're going to call it for today. Have a great day. I will see you on Friday.